Dear students, today we are discussing about bridge structure. Have you seen bridge structure in this slide? I think you can see the bridge structure now. I will show you from Google. Yeah, this is a best example of bridge structure. Component 1, component 2, 3, 4, 5. Suppose we are transmitting a signal from this source node to destination. Okay, what are the possible paths the signal can go through? 1, 4, and then get into the destination, or 2, 5 to destination, or 1, 3, 5 to destination, or 2, 3, 4 to the destination. So that are the possible paths of a bridge structure. This is the typical bridge structure. Okay, so so there are other possible bridge structures available in the website, Google website. You can see several bridge structures. So this is we are considering. Okay, so what is the so there are uh, yeah, there are several bridge structures available in Google. No problem. Anyway, we can refer this one. Okay, so when we refer this bridge structure, what are the possible combinations? Okay, for the system functioning, what are the possible combinations for the system is in functioning stage? Okay, let x1 be the first component state, x2 be the second component state, x3 be the third component state, x4 is the fourth component, x5 is the fifth component. This is the system state. Okay, let us think about the situation that is all the nodes. This can be called as nodes in signal transmission system. So let us call it as node or component. Let x1 be is in functioning, x2 is in functioning, x3 is functioning, x4 is functioning, x5 is functioning. Then the system will be in functioning stage. On the other hand, suppose that x1 is failed, at the same time we have x2 is functioning, x3 functioning, x4 functioning, x5 functioning. Then again system will be in functioning, because a signal can transmit through 2, 3, 4 or 2, 5 paths. Okay, and alternatively, let us consider system component 1 is functioning, component 2 is in failed, then remaining components are in functioning state. Then also the system is functioning. Okay, now we think about the third situation. First component is functioning, second is functioning, third is 0, fourth is functioning, fifth is functioning. Then also system is in functioning. Okay, signal can transmit from the source to destination. Okay, another situation is, it is a there are another possibility, 2 zeros can come. Oh no, this one is functioning, 0 function, system is functioning. Okay, another possibility is what is that? 1 1 1 1 0 1. Likewise, you can find out the all other possible combinations. Okay, all other combinations you can find out. So think about the situation that component 1 is functioning, 2 is 0, 3 is 0, 4 is functioning. Okay, then also system is functioning. Okay, so this vector is called path vector. Okay, this vector is called path vector. That means 1 comma 0 0 1 0, because when we put the values of this vector into the system sector, this function system state will be 1. Okay, similarly we can see that 1 sorry yeah 1 1 sorry 2 2, that is 0 2 0 2 is function for 2 sorry 2 0 5 is function. So component 2 and 5 are working and all other components are in failed state. Then also system is functioning. Now let us so this is also a path. This is also a path vector. Okay, this is also a path vector, and so these two vectors are path vectors. Another situation is, let us consider this one. This one is also a path vector. Okay, so we will have several path vectors corresponding to the system. System is functioning. What is the difference between this path vector and this path vector? When we bring this element to 0, when the fourth element brings to 0, then what happens? Yeah, let us remove that. Let's consider, suppose considering this vector, let us put another color. Okay, what happens when this component becomes 0? Then system will be in failed state. Okay, but in this case, if the component x4 is going to 0, then the system is still working. But in this case, when the component x4 is getting 0, is going 0, then the system will be going to failed state. But in this vector, if the component is in failed, component is failed, x4 the fourth component is failed, then the system is still remains functioning. So what is the difference between these two vectors? Yeah, these vectors are all path vectors because the system function status is 1. At the same time, this path is minimal path. What is the reason? If any one of the component is going to 0, then the system will be going to 0. That means, suppose this is the y vector, this is the x vector. You know that y is strictly less than x because one of the component is in vector sense, in the vector sense, vector y is less than x because one of the component is 0 in y and the same component is 1 in x. So we can write it as y less than x. In this case we have, what is that? In that case we have, what is the occasional v? Yeah, let us take a word file also. In that case we have the system stage. That means, yeah, just put the equation. That means we can say that when y less than x, comma, then what happens? Yeah, phi of y less than phi of x, because it is in this example it is 0. In this example this is 0 and this is 1. Okay, so such, but in the case of vector number 2, that is not possible. This is for the vector number 10. row, when we consider row number 10. Okay, when we consider row number 2, what happens? Y is less than x. What is y here? This is x, and its y is this one. This is x. Sorry. This is x, and the corresponding y is this one. Okay. So in this case also y is less than x, but at the same time phi of y equal to 1 and phi of x also equal to 1. So we cannot say this inequality. Okay. We cannot say, sorry. Case of row 2, this is 1, but so this is not less than, it is exactly equal to. So in row number 2, the vector x is not vector x is a path. X is a path, and this vector is also paths. At the same time, this vector is not minimal path, because if it was a minimal path, we should have phi of y equal to 0. So but in this case, this vector is a path, at the same time it is a minimal path. What is the reason? Yeah, when one component becomes 0, then phi of y equal to 0 and phi of x equal to 1. So such vectors are called minimal paths. So that is formally written here. You can write down from this book chapter. The notations are given here. Okay. Let x indicate the state of the set of components x 1, 1, 2, 3, etc. Then we can define C naught of x is equal to set of all I such that xi equal to 0. The set of all components such that xi equal to 0. In this case we have in this case this is this I means 2, 3, 4, 5. Okay, so C naught of x is 2, 3, 5. This is C1x, and another set is C1x. That is set of all I such that xi equal to 1. What are the C1 members of C1? 1 and 4. Okay, so assume that the structure C comma phi is coherent. So a path vector is a vector x such that phi of x equal to 1. Clearly this is a path vector. Okay, sorry, this is a path vector, and this also a path vector. These are all path vectors. Okay, clearly what is the condition of path vector? A vector x such that phi of x equal to 1. The corresponding path set is denoted as C1 of x. So what is the C1 of x? Yeah, C1 of x is set 1 comma 4. So that is you can find out that path vectors. Yeah. Okay, what are the path vectors? You can say path vectors. 1, 4 is a path vector. 2, 5 is a path vector. 1, 3, 5 is a path vector. 2, 3, 4 is a path vector. 1, 2, 3, 4 is a path vector. 1, 2, 3, 5 is a path vector, etc. We can find out many number of path vectors. What is the condition for path vector? Path vector is a vector x such that phi of x equal to 1. Just to requirement is when we put into phi, we will get the structure function value equal to 1. Okay. So, but at the same time, what is the specialty of this type of vectors? Yeah, these are minimal path vectors, because when one of the component is getting 0, then the system will be going to 0. Okay, so such path vectors are called minimal path vectors. A minimal path vector is a path vector x such that when y less than x, phi of y equal to 0, and the corresponding minimal path set is c1 of x. So we can so what is the path set of minimal path set? Set 1 comma, in this case the minimal path set is 1 comma 4 2 3 4 4. So there are 5 number of minimal path vectors. 2 comma 5 is another path vector, sorry, minimal path vector, minimal path vector. Another minimal path vector is 1 comma 3 comma 5 is another minimal path vector. Another minimal path vector is, look at the figure, just look at the figure and fill the data. Another minimal path vector is 2 comma 3 comma 4. So what is the value? 2 comma 3 comma 4. All other path vectors are path vectors, at the same time they are not minimal. So these are the 4 minimal path vectors of this structure function. Okay. And yeah, we can consider another term, cut vector. What is a cut vector? A cut vector is a vector x such that phi of x equal to 0. The cut vector is a vector such that phi of x equal to 0. When we put the x values, if phi of x equal to 0, then the corresponding x is called minimal cut vector. Okay. And also we have, let us consider the example. This is a cut vector. Yeah, when we put this into phi, we get it is 0. So similarly we can find out several combinations of x1, x2, x3, x4 such that phi of x equal to 0. So that are all cut vectors. At the same time, when we increase the value of this vector x4, that means when we increase this vector, that means we are replacing this value with 1. What happens? It becomes 1. So such vectors are called minimal cut vector. Okay, such vectors are called minimal cut vector. So this is a minimal cut vector. What is the reason? Yeah, this is a cut vector, but when we move at least one of the element from 0 to 1, the system structure becomes 1. So we call it as minimal cut vector. Okay, yeah, here it is defined. A minimal cut vector is a cut vector x such that y greater than x. Clearly, if this is y, this is greater than this one. This vector is greater than this one. Okay, because one of the component is more than the corresponding component. So there is a minimal cut vector. So y greater than x implies phi of y equal to 1. So corresponding minimal cut set is called C0 x. Okay, C0 x. So we have the minimal cut vectors and minimal path vectors of this is the path sets, minimal path set p1 equal to 1, 4, p2 equal to 2, 5, p3 equal to 1, 3, 5, p4 equal to 2, 3, 4. And similarly, in the next slide we can see that what are the minimal 1, 2, set to 1, 2. That means set to 1, 2. Set to 1, 2 means 0, 0, 1, 1, 1. Okay. Another one is 4, 5. Don't worry about this one. This is an example only. Okay. Another one is 135, 135, 5. Another is 234. So 2, 3, 4. So in this case, you can see that when we move at least move to what is that? When we move any one of the failed component into the functioning stage, or when we, what happens in this case? Yeah, in this case we have the system structure is 0, 0, 0, 0. Okay, in this case the system structure is 0. Okay, system structure is 0, but at the same time, yeah, you can see that the system structure is 0. At the same time, when we move at least one of the components from 0 to 1, let us move this component to 1. So what happens? Yeah, the system will be in functioning stage. Okay, suppose we move this component to 1, then system will be in functioning stage. Okay, when we move this to 1, the system will be in functioning stage. When we move this one to 1, the system will be in functioning stage. Okay, so these 4 vectors are minimal cut vectors. Okay, so there are several cut vectors, but these are minimal cut vectors, because when we move any one of the component state from failed state to functioning state, the system will be going from failed state to functioning state. So that is the speciality of minimal cut vectors. So these are the minimal cut vectors of the structure function. Okay, now let us break the system into call the system structure minimal path. Structure. Okay, anyway, think about the minimal path vectors. If at least one of the path is functioning, that means either 1, 4 or 2, 5 or 1, 3, 5 or 2, 3, 4 is in functioning state, then the system will be in functioning state. So at least one minimal path is required for the system functioning. So what will be the structure of the minimal system in terms of minimal path? Yeah, that you can see in this figure. Yeah, it is here, available here. At least one of the path, if at least one of the path is functioning, then system will be in functioning. So what are the paths, minimal paths? 2, 3, 1, 4, 2, 3, 4, 1, 3, 5. So if at least one of the minimal path is functioning, then the system will be in functioning. So we can consider the entire system as, parallel connection of the subsystem consisting of minimal paths. Okay, the entire system can be considered as parallel connection of, because at least one path is required. So that means the system can be considered as a parallel connection of subsystem, where the subsystem consists of the minimal path components. Okay, so what are the subsystems? The subsystem consists of 2 and 3. The subsystem consists of 1 and 4. Subsystem consists of 2, 3, 4. And subsystem consists of 1, 3, 5. So if at least one of the subsystem is functioning, that means at least one of the minimal path is functioning, then we can say that, what we can say? Yeah, we can say that the system structure is functioning. Okay, that is the so we have expressed the system structure in terms of minimal paths. Now think about this individual paths. So this path is in series. 1, 3, 5 is in series. Also 2, 3, 4 is also in series. So 1, 4 is also in series. 2 and 3 are in series. So so each path can be represented as a series subsystem. So what will be the structure? Yeah, for the first path, the structure function is x1, x3, x5. x1 into, because it is a product. For the series system, the structure function is product. So phi 1, rho 1, it is denoted as rho 1. Rho 1 is x1 into x2, x3 into x5. Rho 2 is, it is the theoretical part is explained here. The rho 2 is x2 into x3 into x4. Rho 3 is x1 into x4. Rho 4 is x2 into x3. Okay, clear? So the entire system can be represented as a parallel connection of series subsystem. Okay, so the structure function of each subsystem or each path system can be represented by rho j of x, equation 3.1. It is given in equation 3.1. Okay, so rho j of x is the rho 1 of x is the structure function of the first subsystem. Subsystem in the sense the subsystem consists of first minimal path. So this will be I belongs to pj, jth minimal path. I belongs to pj. That means in the case of first minimal path, it will be 1 and 4. So I belongs to pj xi. You can write, yeah, it is here written here. It is written here. Okay, rho 2 is x2, x3, x4. For the second minimal path, the components are 2, 3 and 4. For the third minimal path, the components are 1 and 4. So rho 3 is x1 into x4. So likewise we can express all the minimal path structures. Okay, and think about that, this is the entire system can be considered as parallel connection of these subsystems. So we can, the entire system structure can be represented as phi of x equal to union j from 1 to p. Suppose there are p number of minimal paths. If there are p number of minimal paths, this is equal to union j from 1 to p rho j of x. But you know that what is the this is just only notation. Its explanation is 1 minus product j from 1 to p 1 minus rho j of x. Okay, so this is the expression of system structure in terms of minimal paths. Similarly, we can consider the system in terms of minimal cuts. So here we have given that, yeah, these are minimal cuts. Okay, if at least one of the what are the minimal cuts we have written? Yeah, 1 2 1 2 what is that? 1 2 1 2, then 3 4 4 5, then 1 3 4 1 3 should be here, I think 1 3 5 will land 1 3 5, then 2 3 4. Okay, this is clear. Okay. Okay, so that can be, if at least one of the, this is the minimal cut. If at least one of the minimal cut is functioning, then the system will be in function. So that is the situation. Okay, 0 1 1 0 1 1 0 0 1. Okay, so if at least one of the component in the minimal path is functioning, the system will be in function. So that can be viewed here. Okay, so we can represent as we can represent as a parallel connection. Okay, 1 2 in parallel, 4 5 in parallel, 1 3 5 in parallel, 2 3 4 in parallel. So if at least one of the component is functioning in this set another component is functioning, then the system will be in functioning. If at least one of the component in each subsystem is functioning, then the entire system will be functioning. So we can represent like this. But what is the specialty of this structure function? It is a series connection of parallel subsystems. What are the parallel subsystems? The components corresponding to the minimal cuts. Okay, the components corresponding to minimal cuts are connected in parallel. So that are subsystems. So the entire system can be considered as series connection of parallel subsystems, where subsystem are the components connected in parallel corresponding to the minimal paths. Okay, so what will be the structure function? This can be denoted as kappa 1 kappa j of x equal to union. Since it is parallel, it will be union I belongs to kj xi. Okay, I belongs to kj xi. So for the first case, it will be 1 and 2 are in parallel. So what will be the structure? 1 minus x1 into 1 minus x2. In this case, 4 and 5 are in parallel. So 1 minus x4 into 1 minus x5. In this case, 1 3 and 5 are in parallel. So 1 minus x1 into 1 minus x3 into 1 minus x5. In this case, 2 3 and 4 are in parallel. 1 minus x1 into 1 minus x3 into 1 minus x4. So 1 minus x2 into 1 minus x3 into 1 minus x4. So this is the structure function of the system in terms of minimal cuts. So if all minimal cuts are functioning, you can see from this figure that if this subsystem is functioning, we need to ensure that all the subsystems are in functioning for the system is functioning. Okay, if at least one of the subsystem are in failed state, the system will not be in function state because it is connected in series. Okay, so what will be the entire structure functions status? Phi of x will be the product of subsystems structures. Okay, product of structures of subsystem. Okay, what is the reason? Yeah, this is in series with this one, this set, and is again series with this set, and it is again series with this set. Okay, so we can represent phi in terms of minimal paths or minimal cuts. That is the speciality of this this section. Okay, any structure function can be represented as like this. That means any structure function, any complicated system can be analyzed. That is the exact that is the exact aim of this section. We can analyze, we can conduct reliability analysis for any system, because any system can be represented as series connection of parallel connection of series system or parallel connection of minimal path sets, or any system can be represented as series connection of minimal cut sets, minimal cut structures. Okay, so we can analyze any system using minimal paths and minimal cuts. That is the specialty of this section. Okay, in reality you can see that if you going to the Google, yeah, you can see that they have represented the system, and they will analyze using this type of diagrams. So what is the use of this diagram? Yeah, they will use, especially engineers will conduct this type of structure function configuration for their system. What is the reason? So they can easily analyze. So everywhere you can see, in electronics, in computer science, in engineering, in whatever be the area we are considering for engineering, in their studies we can see that many number of structure functions, many number of structures and corresponding functions. What is the use of this type of representation of structure function? So it can be easily analyzed as series system of parallel subsystem or parallel system of series subsystems. So this is another example you can see. And so everywhere we can see this type of structures. Engineering. Okay, this is especially we are using this type of minimal path, minimal cut in engineering analysis. Anyway, you write down up to this this example. If you have any doubt, you can we can clarify when we come in live video, no problem. Today I have Bodo's passport meeting, so I am giving you the video of this class. Okay.